will come back. Please recall that yesterday we have learned the input-output relation for many systems has the form of a linear ordinary differential equation like this, with these coefficients b0, b1, etc. being constants. Here x is the input and y is the output. This equation can also be written in this way, where we have taken these y's common here. We have taken y common, and inside this bracket we have a operator. Okay, and what is a operator? That we have learned yesterday. Now this operator, nth derivative, then n minus nth derivative multiplied by this constant, plus so on, plus then this multiplication by b0 operator, everything together is one operator that acts on y, and the result is equal to x. I can also write this equation in this way, where instead of using this symbol ddt for differentiation, I have used the alphabet capital D. And similarly, for the nth order derivative, I have used d to the power n. This is same equation as this one. Now, this is quite a long equation to write again and again. Therefore, I will use a simpler notation, and I will write this long operator with a shorthand symbol ON, O for operator, and this N reminds us that this is a nth order differential operator. So this long equation then can be written like this: On acting on y is equal to x. This is much easier to write. Now please note that this operator On is a linear operator. That means this operator obeys the principle of superposition. So I can write this operator On acting on the sum of y1 plus y2 is same as operator On acting on y plus operator On acting on y2 separately. You can verify this yourself. Anyway, differentiation operation is always linear, and so this is also going to be homogeneous, and I can write On acting on k times y is same as k times On acting on y. That's good. Now Yesterday we have also learned that this kind of systems is linear and time invariant. Now suppose this input is given and we want to find the output. But we have learned that to get the output, we will also need n number of initial conditions or boundary conditions, which look like this. The value of the output y at t equal to 0 should be known or given. The value of the derivative of the output at the beginning should be given, and so on. Now, if we do not know these initial conditions, we only know the input, then we cannot get the output uniquely or unambiguously. If initial conditions are not known, then we can have multiple solutions for the same input x. Why is it that there could be multiple solutions for the same input x? To answer this question, let us first observe that whenever we have multiple solutions, say we have two solutions, call them y1t and y2t, for the same input, call it xt. That means y1 and y2, both of them satisfy this equation that On acting on y1 will give us x, and also On acting on y2 will give same input x. If I call this equation 1 and this equation 2, then from 1 minus 2 we shall get On acting on y1t minus y2t is equal to x minus x, which is equal to 0. That means this is a signal which gives 0 when acted by this operator On. So this is called a complementary solution or complementary signal, CS in short. Let me define that given a differential equation On acting on y is equal to x, if we have a signal y0 such that On acting on y0 gives 0, then y0 is called a complementary solution to this given differential equation. So what we have seen is that whenever we have more than one solution or at least two solutions, we will definitely have a complementary solution. That means a signal which will give 0 when acted by this operator when. The reverse is also true, that whenever we have a complementary solution, we will have more than one solutions. Given the differential equation when y is equal to x, and given the input x1, if y1 is one particular solution, that means y1 satisfies this equation when y1 is equal to x1. Under this situation, if there is a complementary solution y0 such that when y0 is equal to 0, then we can have another signal y is equal to y1 plus k times y0, and this new signal y will also satisfy the given differential equation. That means this equation, call it equation 3. You can check it for yourself, putting y equal to y1 plus ky naught here in this equation. So we have y1 plus ky naught. This is the left hand side, and this will be equal to on y1 plus k on y naught. Now the first term is equal to x1 and the second term gives 0, equal to x1, or the right hand side of this equation. So we have shown that if y0 is a complementary solution, if there exists a complementary solution and y1 is any particular solution, then we can construct many other solutions of this form y1 plus ky0, where k is an arbitrary number. So for any value of k, this y will still be a solution. Now let me generalize. For the system on y is equal to x, and for the input x equal to x1t, if y1 is one particular solution or any one solution, one or any particular solution, that means on acting on y gives x1. So x1 y1 together satisfies this differential equation. And if we have complementary solutions, many complementary solutions like y01, y02, say up to y0n, which means that when y01 is equal to 0, and ONY0, n is also equal to 0. Then any signal of this form y is equal to y1 plus say k1 y01 plus k2 y02 plus kn y0n will also be a possible output corresponding to the input x1. And this way we can construct many other possible solutions. This k1, k2, kn, they are arbitrary constants, and we can take any value for k1, k2, kn. And please note that this is the complete, exhaustive list of possible solutions for the same input x1. There can be no other signal different from this form which is a candidate solution or candidate output for this input x1. That is not possible. All possible solutions can be written in this general form. Now, with this idea in mind, I will tell you a recipe how to find the output of such a system given the input. So here is the recipe to find the output given the input and the initial conditions. So suppose the system is defined like this: ONY is equal to x, the input is given as x equal to x1, and boundary conditions like this: y0 equal to something, and so on. Now, step 1, find any particular solution y1 which satisfies this system equation with the input x1. So find any one solution such that ONY1 is equal to x1 without bothering about the boundary condition. So the boundary conditions or initial conditions need not be obeyed. Now, how to get such a y1, that is what we shall see later. Next, step 2, list all the complementary solutions y01, y02, etc. such that ONY01 is equal to 0, ONY02 is equal to 0, etc. And how to get all the possible complementary solutions? That is what we have seen yesterday. Let us recall that ON is same as this operator, and yesterday we have learned how to factorize this operator. To factorize we will first write a polynomial dn plus b1 d plus b0, and we will equate it to 0. We will find the roots or the solutions of this polynomial equation, call them a1, a2, etc. We can have a total of n number of roots, but some of these roots can be repetitive, and then you can write this as ddt minus a1 ddt minus a2 and so on. If these roots are repetitive, say a1 repeats n1 times, a2 repeats n2 times, and say the last one is ddt minus ap, which repeats np times. This total of n1 plus n2 plus np should be equal to n. That is the total number of roots of a nth order polynomial equation. Okay, and then we have seen that for this operator, which we are calling as on, we have signals of this form: e to the power a1t, e to the power a1t multiplied by t, then t to the power n1 minus 1, e to the power a1t. All these signals, when they are operated by this operator, will give 0, because particularly this first part will give 0 when they act on any of these signals. Similarly, e to the power a2t or e to the power a2t multiplied by t to the power say k2, where k2 should be less than this n2, then all these signals will also give 0 when they are acted by on. Therefore, these are the complementary solutions, and in this way we will have a total of n number of complementary solutions. That is also we have seen yesterday. So in this way we can complete our step 2, that is we can find the list of all complementary solutions. Now step 3, you should recognize here that any and all possible solutions, all possible outputs can be written in a general form: y is equal to y1 plus k1 y01 k2 y02 plus ... here also plus up to kn y0n, where y1 is any particular solution, any solution that you have found in step 1 somehow, and y01, y02, these are these signals, these complementary solutions. Now this is the complete list of all possible solutions, but given an input at one moment, you can get only one output. You cannot get all these possible outputs together. So we have to find which output we shall get, and for that we will need to use the initial conditions that we have not used so far. So step 4, find the values of k1, k2, kn using boundary conditions. Note that any and all possible values of k1, k2, etc. will satisfy the given differential equation, but only one particular set of values will satisfy the initial conditions as well. Which set of values? That we will find in this way. So this is the general equation for the all possible outputs. Call it equation 5. So from equation 5 we have y is equal to y1 plus k1 y01 plus kn y0n, where y1, y01, y0n, all of them are known, only these constants are unknowns. Now let me put t equal to 0 in this expression of y. So here I actually have yt. Now let me put t equal to 0, then the right side becomes like this. And this value is known or given in the boundary conditions, right? Next, from here, let us differentiate this equation and write dy dt is equal to ddt of y1 plus k1 times ddt of this term y01 plus other terms up to kn ddt of y0n. This is what I get by differentiating this equation. And from this, now if I put t equal to 0, at t equal to 0, similarly right hand side evaluated at t equal to 0 plus k1 this term evaluated at t equal to 0 plus so on. This is also known or given because this term is given in the boundary conditions. So this way you can differentiate this equation once again and write the second derivative of y equal to the second derivative of y1 plus k1 second derivative of y01 plus the other terms up to nth term, and then you put t equal to 0. This is the left hand side, and the right side is like this. Plus other terms, and this is also known because this value is given in the initial conditions. So in this way you can differentiate this equation n minus 1 times and put t equal to 0, and then you will get one equation here where k1, k2, kn, these are unknowns, and everything else is unknown. Similarly, in this equation again k1, k2 will be unknown, everything else are known, and this way by differentiating this equation n times you can n minus 1 times you can generate n number of equations in terms of this unknown k1, k2, kn. Okay, so let me call these equations as E1, equation 1, this is as equation 2, this is as equation 3. So we have n equations and n unknowns, which are this k1, k2 up to kn. So we can solve these n equations together to find the n unknown values. Solve this to get k1, k2 up to kn. So that was the recipe how to get the output starting from the system equation and given input and given initial conditions. Let us now learn a few new concepts like forced response, natural response. Consider a system when y is equal to x. Now let us consider a few different situations. Number 1, when the input x is equal to 0 and also the initial conditions are all 0, y0 equal to 0, y dot 0 equal to 0, and so on, all of them 0. So that means 0 initial conditions. What will be the output yt in this case? It is easy to see that yt will be equal to 0. You can check it for yourself by putting y equal to 0 here. The left hand side will be 0, right side is also 0, so that satisfies the system equation. that also satisfies all the initial conditions. So this is definitely the output without any ambiguity. You can check it also in this way, what we did yesterday, starting from all 0 initial conditions and input also 0, calculate the output at next time instant delta t, you shall get 0. All the other derivatives also will be 0, and this way if you calculate output at subsequent time instants, you will get all 0. Now consider the next situation when you have non-zero input but all 0 initial conditions. You will get some output, and whatever output you get, let me call that yft, say. Okay, so this is the second situation, and then consider the third situation when you take 0 input but non-zero initial conditions, like y0 equal to some value, call it v0, y dot 0 equal to some value v1, and so on. Under this condition, what will be the output? Will it be 0? No, it cannot be 0, because then it will not satisfy these initial conditions. So you shall get some output which we will call at yn, say. Please note that yn must be a complementary solution of the given differential equation. That means yn should be equal to 0. That is because x is equal to 0. Now let us consider a fourth situation when you take input to be non-zero. To be more specific, let me take input to be same as the input which we had in this situation. Call this x1. So here also input is x1, and also initial conditions are non-zero. To be more specific, I will take them same as this situation 3. So y0 equal to v0, y dot equal to v1, and so on. Now what will be the output? You can easily see that in this case output y will be equal to yf plus yn, where yf is this output when the input was non-zero but initial conditions 0, and yn is this output which we got with 0 input but non-zero initial conditions. You can check it for yourself that if you put here yf plus yn in the system equation, then this will be equal to O of yf plus O of yn, and O of yf should be equal to x1 because yf was the output for x1, So the first term here will be x1 and O of yn will be 0. So this satisfies the given differential equation. Also, let's check the initial conditions. So if we find the value of yf plus yn at t equal to 0, that will be same as yf0 plus yn0, and now yf0 should be equal to 0 because yf was the output here for 0 initial conditions. So here we had yf 0 equal to 0 and other derivatives also 0. But in situation 3, yn 0 must be equal to v0 and y dot n0 should be v1 and so on. So here when we have the sum, the first term becomes 0, second term is v0, so this also satisfies the given boundary condition. So we conclude that if you have both non-zero initial conditions and non-zero input, then the output will be the sum of the two outputs yf and yn, where yf is the output for the non-zero input and zero initial conditions, and yn is the output for zero input but non-zero initial conditions. It is like a superposition. Now let me define this output yf as the forced response which is generated by non-zero input. Response means output, F for force. Here we are thinking the input as the driving force of the system, and therefore we are calling this as the forced response, or the response generated by the input only. And this response yn is called natural response, N for natural, and this is what we get with no input, only by virtue of non-zero initial conditions. So this is a spontaneous output that you get without any input. Let's take our favorite example. This object as the system, force is the input and displacement being the output. You can get an output without any input or x equal to 0, 0 force, if the initial position of the object or initial velocity of the object is non-zero. That is what we will call as the natural response. Again, if the initial position and velocity are 0, then if you give force, you can get an output. That is what we will call the forced response. And if you give a force and simultaneously also the initial velocity and initial positions are non-zero, then the output that you will get will be the sum of the previous two outputs. and if you give no force and also the initial conditions are 0, then the output will be 0. Okay, it is now time to learn actually how to solve a differential equation, and we shall start with a simple first order equation. Suppose the given equation is dy dt minus ay or ayt is equal to xt. To solve it, we shall use a trick. We shall multiply both the sides of the equation with e to the power minus at. This is called an integrating factor. Why e to the power minus at? Because of this minus a. After multiplication, we will have dy dt multiplied with e to the power minus at, then ay multiplied by e to the power minus at, and the right side is equal to x e to the power minus at. Now note that the left side of this equation can be written as d dt of y e to the power minus at. You can verify this by differentiating this product using the product rule. Right side as it is. Now we shall integrate both the sides with respect to time. Let me do the integration from time 0 to time t. Then the left hand side will become y e to the power minus at at time t and at time 0, and the right side is as it is. From this we can write y t e to the power minus at minus y0 e to the power minus a0 is equal to whatever we have in the right side. From this we can get yt e to the power minus at is equal to this right side term which is here, and bringing this term to the right, so we shall have y0 e to the power 0 is 1, and from this you can get the output y by dividing with this term, and the result will be e to the power plus at x e to the power minus at dt integrated from 0 to t, plus here we will have y0 e to the power a t. So this is the solution. Now note that this solution has two terms, one here and another here. Let me call this term as yft and this as ynt. Now you note that ynt does not depend on input. This depends on input. This term will be 0 if the input is 0, whereas this term need not be 0 even if input is 0. This term depends on the initial condition y0. However, this term does not depend on the initial condition. This term will be 0 if the initial condition y0 is equal to 0. So therefore, you can clearly recognize that in the solution we have obtained, we have clearly two terms. This term is by definition the natural response yn, and this is by definition is the forced response, and the total output is the sum of these two. So we have learned how to solve a simple first order differential equation, and here is the solution. But this is not quite complete because we will have to simplify this integration, this first term, or yf, which is given by this integration. And we also have e to the power at here. Now to simplify this, we need to know the input x, the functional form of the input. We shall assume the input to be of the following form. Xt is equal to some polynomial like k0 plus k1t plus k2t square plus dot 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 up to knt to the power n whole multiplied by with a exponential e to the power at. Or let me take e to the power bt, since a is already used here. Okay, so you can then consider some special cases of this form. You can consider xt equal to pure constant. That means b is equal to 0 here, and then k1, k2, they are also 0. Only k0 is present. So that input being constant will be a special case of this general form of input that we are considering. Similarly, you can have a pure polynomial. That means set b equal to 0. So only this polynomial term will remain and this part will become 1. You can make it pure exponential by setting k0 equal to 1 and k1, k2 equal to 0. So this will be some special cases of this general form of the input. Later, we can also consider sinusoidal inputs, and that is because we know that sin omega t is equal to e to the power j omega t minus e to the power minus j omega t divided by 2j, and cosine omega t can be written as e to the power j omega t plus e to the power minus j omega t whole divided by 2. So this type of sinusoidal or cosinusoidal inputs can be broken into pure exponential inputs. So if we have a sinusoidal or cosinusoidal input, then we can break it into two pure exponential inputs, and since the systems that we are considering are linear, then to get the output for sin omega t or cosine omega t, we need to calculate the output separately for this part, this exponential and this exponential, and then add them. So by virtue of linearity, later we can also solve the output for sinusoidal or cosinusoidal inputs. So we shall restrict ourselves to this particular form of the input. And now with this input form, let us simplify the expression for the forced response here. So let me start with yf is equal to e to the power 80 x e to the power minus 80 dt. Now let me put the expression for x, which is this polynomial multiplied by e to the power bt, then this e to the power minus 80 dt. Then here let me now club these two exponential terms together and write it as b minus 80. Then we can have two possible cases. Case 1, when b is equal to a, then you can yf is equal to e to the power 80 integration of this polynomial and this term will be 1. So that's it. Now integrating a polynomial is very easy. This integration will result in a polynomial again, but with order n plus 1. If this is a polynomial with order n, then the integration will result into a polynomial of order pn plus 1. Let me write that in this way. A polynomial pn plus 1 t. And also let me denote this polynomial as pn t, a nth order, nth degree polynomial. Now let me put a prime here because this p and this polynomial, they are not same. Here the exact form of this polynomial or the coefficients inside this polynomial can be found, that will depend on this k0, k1, etc. but I'm not going to do that. I am just writing that the final result will be a polynomial of n plus 1 degree multiplied by e to the power at, because finally later I will not need the exact form of this polynomial or the detailed coefficient values. So let me keep it like a polynomial multiplied by e to the power at. So that is case 1. And the second case is when b not equal to a. If b is not equal to a, then let me write yf again. Yf is equal to e to the power at integration of this polynomial. Let me use the shorthand notation pnt and e to the power b minus at dt. Now I shall evaluate this integration by parts. So yf will become e to the power at. Then let me consider this as the first term and this as the second term. So integration by parts gives first term Pn, integration of the second e to the power b minus a t divided by b minus a, minus integration of the derivative of Pn d dt, or let me write simply p dot n, and this term e to the power b minus a t divided by, but this divided by term I can write outside, 1 over b minus a, and this will be evaluated from at t and at 0. This is 0 to t. Next, we can write this as e to the power at, and then this first term will become a polynomial of degree n, not necessarily the same polynomial, call it p prime, multiplied by e to the power b minus a t, and this factor is absorbed inside this polynomial. Then this 1 minus b minus a, 1 by b minus a, integration of this part, let me keep it as it is, now let me multiply this e to the power at with this term, so I will have p prime n, then e to the power minus a plus a will cancel and bt will remain. Then this term 1 e to the power at divided by b minus a, this and this, and then I have to integrate this term, and I will apply integration by parts once again. So if I do that, take this as your first term, so you will have the first term integration of the second minus the integration of the derivative of this, which will become p double dot n, and then this term let me write b minus a outside dt, here also dt. So we have applied integration by parts once again. Now we can write this as this first term as it is, then let me multiply e to the power this part inside, so we will have p dot n and whole divided by b minus a whole square, this one and this one, then e to the power plus a minus a cancels, only e to the power bt remains, then minus minus plus e to the power at divided by b minus a whole square, and then you have this integration term. Okay, now here you see that, let me keep the first term as it is. The second term is the derivative of a nth degree polynomial. So that will be a polynomial of degree n minus 1. So I can write that as p double prime some new polynomial of degree n minus 1, and this constant b minus a could be absorbed in the coefficients of this polynomial. Then e to the power bt as it is plus this term. Now your homework is to apply integration by parts once again, third time on this term. Okay, if you do your homework, then you shall get these two terms as it is, and you shall get a term like the double second derivative of p. So you shall get another polynomial with degree n minus 2 because of the second derivative. Okay, and these constants can be absorbed inside the polynomial. Call this new polynomial p triple prime, and then you shall get something like e to the power bt and so on. Now you can repeat this process of integration by parts again and again. No worry, the process will definitely terminate, because every time you do integration by parts, you see the here we had p dot, next here we have p double dot, and therefore the degree of this polynomial is reducing, and finally this will become a constant. If you differentiate a polynomial again and again, after n number of derivatives, it will become a constant. So at that point, your process of repetitive integration by parts will stop, and by that time you will have many other terms like this: nth degree polynomial, n minus 1th degree, n minus 2, and so on. Finally you will have maybe some constant times e to the power bt. Now if you combine all these terms together, you can write it as one polynomial of degree n, call that p bar, multiplied by e to the power bt. E to the power bt is common everywhere. Now if you combine a n degree polynomial, n minus 1 degree polynomial, and so on, the result will be a n degree polynomial. So this is how the solution will look like. Please note that the exact expression of this polynomial or the exact coefficients inside this polynomial can be found in this way if you do this carefully, keeping track of all these coefficients throughout, then you will find the exact expression of this polynomial. But I will not need that finally, so I will stop by claiming that the final solution will be a nth degree polynomial multiplied by e to the power bt. So we have started from this expression of the forced response here, and we have chosen x to be of this form, a polynomial it is written here, x is a polynomial multiplied by e to the power bt, and when we put that value here, we get two possible cases. In one case, if b is equal to a, then the final solution will be like this: e to the power 80 multiplied by n plus 1th degree polynomial. This you can also write as e to the power bt p prime n plus 1 t, because b is equal to a. And if b is not equal to a, then the final solution will be e to the power bt multiplied by a polynomial of degree n. So the difference between here this case and this case is in the degree of the polynomial. Here n plus 1 and here n. So that's it for today. See you tomorrow again.